Welcome to the lecture on goodness of fit tests and assessing sample dependence. So, we have been introduced about the fit tests, and as we know that fit tests are providing the guidance for evaluating suitability of a potential input model. So, in this goodness of fit test, normally we test for the uniformity, and we have seen that the sample size is important. Based on the sample size, we have different type of tests which are used to see that the distribution or the data which is there, whether it can be said to be forming a uniformity, having uniformity or not. So, you have some hypothesis test, null hypothesis is there, whether it is rejected or it is accepted, that depends upon the calculation of the parameters. So, we have two types of tests, chi-square test, and you have the that is chi-square test, and then you have Kolmogorov-Smirnov test. So, these are the two tests which we have earlier discussed in brief. So, what we have seen that the chi-square test is basically it is formalizing the idea of comparing histogram of data to shape of the candidate density or mass function. So, from the histogram you can have you can see that what is the shape of the density or mass function, how it looks like. You will have the data based on that, as we have seen you draw the histograms, and from there you can have a feel about the shape of that. Now, this test is valid only for large sample sizes. So, for both discrete as well as the continuous distribution assumptions, and when the parameters are estimated by maximum likelihood. So, normally we go for whenever we have the large number of sizes, sample size, and also we need to have the calculation of parameters. In those cases we use the this chi-square test. So, because that affects the degree of freedom calculation, which basically we have to know for getting the table value. So, what we do is that basically we begin by arranging the n observations into set of k class intervals, and then the chi0 square. So, that basically is approximately following the chi-square distribution with k minus s minus 1 degree of freedom. So, this s where it is the representing the number of parameters of the hypothesized distribution. So, we get these value first, the parameter values, and this parameter value, as we know, what we see, we have already seen that this will be basically summation y minus ei of square by ei. So, it will be from I equal to 1 to k. So, you have k class intervals. So, you have n observations into k class intervals. So, what we do here is you have the class interval, you arrange the data in those intervals. This is the observed frequency OI, and this is the expected frequency if you are going to fit for the uniform distribution. So, in that case this will be IPI basically. So, that way you have the IPI value, and then ultimately you are doing this, you are dividing it with EI, and then you take the summation of that. So, you get this I0 square, and then that value you are basically comparing from the table with this k minus s minus 1, that much degree of freedom. So, this with that degree of freedom you calculate the value from the table. Now, this value should be less than the value which we calculate from the table. Then we say that this hypothesis is not rejected, I mean the null hypothesis. So, we should not reject that, we can say that this data is forming a uniformity, or it is the uniformly distributed. Now, in this case you have also to see that your sample size normally there is certain guidelines, and sample size and number of intervals. So, how many number of intervals should be there? So, for that, depending upon the sample size, so if the sample size is 20, you do not use this test. Normally your sample size should be larger. Only when the sample size is large you use this test. If the sample size is 50, the number of intervals can be 5 to 10. Similarly, if it is 100, you go from 10 to 20, and if it is more than 100, then you go from under root n to n upon 5. So, this is what normally is accepted, and as we see that the value of chi0 square, it has to be less than the critical value, then the hypothesis assumes that random variable conforms to distribution assumption with parameters given by the parameter estimate. Now, the thing is that size of EI, it is also said that it should be normally ranging from 3 to 5. So, and when this value is less, in that case you can combine it from the adjacent cells, either above or below, you should combine them. So that you get ultimately you have less number of data intervals. Now, if the distribution is discrete, then in that case every data should be the class. Okay, so every data will be a class interval, and in that case, as we have seen that if the frequency is less in some cases, in that case you can combine the adjacent classes, so that you get adequate number of frequencies. So, this is normally practiced in the case of this chi-square test. Now, let us see, you are doing for a Poisson sample. So, if we do the chi-square test for a Poisson sample, we have so we are dealing with the same problem which we have discussed, the number of arrivals and mean number of arrivals on every day. So, we had the data arrivals per day and frequency, So, you have arrival per day 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then more than 11. So, these are the arrivals per day data, and this data was seen, the frequency was calculated as 12, 10, 19, 17, then 10, 8, 7, 5, and further 5, 3, 3 and 1. So, as we see that this type of data is given to you, and you have to use the test to see the uniformity. Now, in this case we have already computed alpha estimator as 3.64. So, we saw that alpha estimator is nothing but x bar, and for that you are computing the product and added all together. This is 364 divided by 100. So, you are getting 3.64. Now, in that case, now you are having this data. So, you will be having xi and in that case you will have OI, EI and further summation of them. So, you will have XI and OI, EI, and ultimately you have to compute OI minus EI square by EI. So, you have the values as we see, you have the values as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So, once you have these values, OI as we see, you have again 12, 10, 19, 17, 10, 8, 7, 5, 5, 3, 3, 1 and expected frequency it will be IPI. So, in this case your expected frequency. Now, how to get these expected frequencies? Now, since it is a Poisson distribution, so in that case what you do is you compute the probability value. Now, for this Poisson distribution, as we know that probability distribution function tells fx will be alpha raised to the power x and then e raised to the power minus alpha divided by x factorial. So, what we see is for exponential distribution, so for Poisson distribution, we get fx as probability mass function will be e raised to the power minus alpha into alpha raised to the power x upon x factorial for x equal to 0, 1, 2 and all, and it is 0 otherwise. So, that we know this, that this is the probability mass function for the Poisson distribution, and we know this alpha estimator 3.64. So, when the x value is 0, in that case you get here e raised to the power minus alpha. So, this way you are getting the values. So, in this case if we get the probability value, this value will come out to be 2.6. Now, what happens, you are getting, this is nothing but P0. So, that will be from here and that value is coming as 0.026. So, 0.026 will be multiplied with 100 and that you get as 2.6. Similarly, for 1, so for 1 again you are putting it here as 1. So, for 1 what is the probability? That is the expected probability. So, this will be coming as 9.6. So, for in this way you are going to calculate this probability value for all these values by placing the value of x here and in this way and multiplying it again with 100. So, you are getting, so once you do that calculation you are getting the values. For 2 it is 17.4, for 3 it is 21.1, for 4 it is 19.2, for 5 it is 14 and then it is 8.5 for 6, 4.4, you have 2, 0.8, 0.3 and 0.1. This is the percentage of probability. This is the 2.6, this is 1.6. So, out of 100 if you have this as the frequency which is observed and this is the expected one, because the process is Poisson. So, you get this. Now, based on that you will calculate this parameter. So, this will be 12 minus 2.6 square divided by 2.6. So, this way your value. Now, the thing is that in this case as we see that we have to see that how we can see you have to get, maybe try not to see so many intervals. So, we will try to combine some of them. So, if we combine here, it will be something like 12.2. So, it will be 12.2. Similarly, on this side it is getting low. So, you can combine all them. So, 6.6, 7.4, 7.7 and 7.8. So, it will be coming as 7. So, we are going further to combine all of them. So, it will be coming as 4.4 plus 2 says this is 6.4, 7.2, 7.5 and 7.6. So, this is coming as 7.6. So, as we have seen that we can combine certain intervals, we have to combine, we have not to take very less or very more, and then further you are finding the values. Now, in this case it will be 22 and this is 12.2. So, 22 minus 12.2 square. So, that will be something like 9. So, the 2.9 plus 9.6, it is coming out 2.6 and yes, it is 12.2. So, further you can do the calculation and that will be close to 7.87. So, it will be 7.87, further it will be 0.15, then you have 0.80, you have 4.41, you have 2.57, you have 0.26, and then for all of them together you are getting the value as 11.62. So, what we do is here we take it as 22 and this is 12.2. Similarly, here you have 10 plus 13, 16 and 17 and this is 11 and this is 7.6. So, we take this. So, once we get that, the summation of OI minus EI square upon EI, and this comes out to be 27.68. Now, this is chi 0 square, this value is, this is the value which is coming out to be 27.68. Now, we have to see it from the table. Now, from the table you have to get, so from table, that table was shown in the earlier lecture. Now, from table you have to see the value, and if we take that 0.05 level of significance as 0.05 and degree of freedom. Now, degree of freedom is k minus s minus 1. So, you have intervals of k, you can see here 1, 2, 3, 4, 5, 6 and 7. So, you have 7 intervals k minus s. So, you have the parameter which is estimated, that is 1, you have calculated that alpha estimator. So, it is 1 and minus 1. So, that is 5. So, from the table you have to calculate this chi-square value for 0.05 to and degree of freedom as 5, and that value is coming out to be 11.1. What we see is the value which we calculate, this chi 0 square, that is 27.68. Now, this is basically larger than this value, whereas for passing the uniformity test it must be lower than this theoretical value or from the table value. So, since it is not less, it is not passing that test. So, we say that it is not uniformly or it is not distributed. So, it does not pass that uniformity test in the case of this data. Now, the thing is, next case is that many a times we have to see that when we take the intervals, it should be for that interval which should have equal probability. We should do the test for those intervals where there is equal probability. Now, the thing is that is why the test of a continuous distribution, in that case it will be better if we take the class interval equal in probability rather than equal in width. So, we take equal in width, whereas we should take equal in probability. So, we should take that those intervals which is expected to have the equal probability. Now, in that case you must know the point where to take that. So, interval, for that interval you must have those endpoints known to us. So, probability associated with each interval should be such that the power of the test of given size is maximum, means the power of test means the probability of rejecting a false hypothesis. So, this way, I mean, accepting a good thesis, good hypothesis is maximum in that case. So, that is power. So, you should take the interval in such a manner that you must have the maximum probability of accepting that particular hypothesis or so. Now, how can we proceed for such cases where you have the equal probability? So, we will see that. So, we will see the chi-square test. So, in that case, as we have seen that in such cases of the test with equal probability, now in those cases as we have seen that the expected frequency EI, it is normally equal to I into PI, and that should be, if we take the maximum number of class intervals, in that case it should be more than equal to 5. So, if we take that case, so if we take, so EI is basically EI which is given as IPI, and if you take the maximum number of intervals, in that case it should be more than equal to 5. Now, so it will be written as n by k, it should be written as more than equal to 5. So, n by k, how it came? No, actually EI has to be NPI. So, EI equal to NPI. So, and PI is equal to 1 by k. So, that is why n into 1 by k. So, n by k is more than equal to 5. It means k has to be less than equal to 5 by n, n by 5. So, k should be, what should be the class interval size? So, k class interval, so k should be less than equal to n by 5. So, if you have, if you know n, it should be, so n by 5 and less than that, the k should be, number of class intervals should be less than that. Now, suppose you have the 50 number of data, that is n is 50, in that case k should be less than equal to 10 or so. Now, suppose we take example of an exponential distribution with lambda as 0.084 and you have n as 50 observations. So, how to find the interval? Now, in this case we do not know, we have the data, from that data we got the x bar. So, you get the sample mean, from there you get lambda estimator, that will be 1 by x bar. So, for exponential we know that we get that lambda estimator as 1 by x bar. Now, in that case what should be the interval length? What should be the upper and lower limit of this interval, every interval, so that the probability is normally equal. So, as we know that you have, in this case what we do is we first of all find the CDF. So, we find the CDF as f of, so if the AI is representing the end point of ith interval. So, suppose A1 will be the end point of the first interval, A2 will be the end point of the second interval. So, it will be starting from A0 to A1, A1 to A2, A2 to A3, like that. Now, if we take this, so in this case, in the case of 50 observations, k has to be less than equal to 50 by 5, that is 10. Suppose we take 8 intervals. Suppose we take k as 8. So, in that case the EI value will be going as 100 by 8, means everything will be 0.125 probability will be there, 12.5%. Now again here FAI we will, so if we write the cumulative distribution function, FAI will be written as 1 minus e raised to the power minus lambda AI. So we know that the cumulative distribution function is Fx equal to 1 minus e raised to the power minus lambda x. So that is how FAI will be 1 minus e raised to the power minus lambda AI, and this AI should be basically, we have to get the expression for it, and this AI, it will be basically I into P. So this will be IP equal to 1 minus e raised to the power minus lambda AI. Now every time we go, you will have these values. So in every class, so IP will be equal to 1 minus e raised to the power minus lambda I. Now we have to solve this, and once we solve it, we get the values as A equal to minus of, so we get we can have the expression more simplified. So we will have e raised to the power minus lambda AI will be equal to 1 minus IP. So in that case we get minus lambda AI as ln of 1 minus IP, and AI will be minus of 1 by lambda into ln of 1 minus IP. Now as we move from interval to interval, this AI has to be calculated so that the probability is equal in every interval. So in that case, as we see, A0 will be always 0, and A8, if you have 8 intervals, A8 will always be the infinity. So if you take the first interval, I will be varying from 1 to 8. So when we go from, for the first interval, the lower limit is always 0, and the upper limit of the last interval will always be infinity. So what we see is that for all lambda, A0 is 0 and AK is infinity. So that data is there, the condition is there with us. Now what we see, that since we know the lambda, and every time we go in the first interval, now this is because we have 8 intervals. So for the first interval, this value will be 0.125. So in that case 1 by 8, so P will be 1 by 8 and I is 1. So for the first one, so A1 will be minus of 1 by lambda, lambda is given to you, and lambda is given as 0.084, so it is 0.084, and then you do it ln of 1 minus 0.125. So this value is basically computed, and this you get as equal to 1.590. It means you are going to have the first data, first interval as from 0 to 1.590. The second interval for that will be A2, and A2 will be minus 1 by 0.084, and in that case it will be ln of 1 minus I is 2 now. So 1 minus 2 into 1 by 8, P is 1 by 8, you have 8 intervals. So it will be 2 by 8, that is 0.25. So ln of 0.75, and then you do that. So this way you get the value as 3.425. So this way you get the different kind of, the ranges A1, A2, A3. If you compute further, you get A3 as 5.595, A4 as 8.252, and so on. So for such typical problem, we can calculate the A1, A2, A3 like that. Next is the assessing sample independence, we have discussed about the uniformity check in the case of sample, how to check the sample independence. So, most of the methods, statistical methods, assume that the data which have been taken, they are independent, and if they are not, then these methods which we use to calculate the estimators or so, they are invalid. So, we are assuming that the data is independent. Now, you need to say, you need to check the dependence or independence of the data. So, for that you have the plots, and these plots basically tell us, and heuristic plots are there which tell us that whether the data can be said to be independent or they are dependent, they are correlated, and you have even formal statistical tests like run test or so. So, we will talk about some number of plots. What are the plots? So, one of them is correlation plot. So, in the correlation plot, what we do is we find the correlation. Correlation is nothing but we have, if you have the random number xi and xi plus j, you have the time varying, the data is there. In that case, we define the correlation rho ij, and that will be basically depending upon the covariance between the two, and then it is further divided by the variance. So, that is, that variable is rho ij. So, this rho j or this correlation of from I to j, so that is computed, and once you compute that, that is plotted. So, once you plot that, it should be basically near to 0. If this value is near to 0, they are said to be independent, and if they are plus 1 or minus 1 close to that, then they are said that they are not independent. So, what we do is we find, in that case, when we go for the correlation, we find this correlation as, so we find rho j as C j estimator divided by S square n. So, this is the covariance. We will discuss later how this covariance is computed. Cj square is computed. This is Cj square. Cj is computed as summation of I equal to 1 to n minus j, and then it is xi minus x bar n, and similarly xi plus j minus x bar n, and divided by n minus j. So, if you start from I and go up to I plus j, in that case what is the correlation between them? For that you get the covariance and then divided by S square n. So, this is basically Cj. This is actually the value of Cj. So, Cj is computed using this formula, and once you get the Cj, then you get divided by S square n. So, you get the correlation, and once you get the correlation, then you plot it. So, you are plotting and plotting this correlation value. So, you are plotting with j. So, you will be plotting like you will have j on this x axis and you have rho j on the y axis. So, this is 0, this is the positive one and this is the negative one. So, in this, if the data is like this, it is fine, they can be said to be that they are not related, they are independent, otherwise they will be said to be correlated. So, that it should be independent. Similarly, another diagram is scatter diagram. In that scatter diagram, what we do is we plot xi and xi plus 1. So, we have the xi and we have xi plus 1, both are plotted. Xi will be here on the x axis and xi plus 1 will be on the y axis, and if it is completely distributed uniformly, then we say that it is scattered randomly, then it is, we say that it is having no correlation, and if they are having some slope positive or negative, in that case we say that they are basically positively or negatively correlated. So, this way this scatter diagram is also used for assessing the sample independence. Thank you very much.